All right, so let's look at an introduction to kinetics. Kinetics is the study of the rates of a reaction. All right, so if we have a reaction, A plus B, it may yield something like C plus D. We know that some reactions go to completion, and we spent the majority of our honors chemistry time assuming that reactions went to completion. But towards the end of our time together in honors chemistry, we learned that some reactions, and really most reactions, do not actually go to completion. And we call that equilibrium. And we talked about the rate of the forward reaction equal the rate of the reverse reaction. Okay. All right, and this is where the rate of the forward equals the rate of the reverse reaction. And therefore, our concentrations at equilibrium for the reactants and our concentration of products at equilibrium do not change in a given time. All right. If a reaction goes to completion, we know that our concentration of our reactants is going to equal 0 at a given time. If we do not go to completion, we reach equilibrium where reactant and product concentrations at equilibrium do not change. So we can look at a graph here. And if we were to graph a reaction and we were to graph their concentration versus the time, reactants are being used up, so their concentration will decrease. Products are being made, so their concentration will increase. And we can describe this rate as the change in concentration over time. And we're going to go into a lot more detail about this concept in another lesson. We can determine this concentration experimentally using Beer's law. Beer's law is a method to determine concentration. And we are going to use light and absorptivity of a solution in order to determine that. All right, so let's take a look here at what Beer's law means. So let's go into a little bit more on Beer's law. And we're going to start with these notes with some drawings, okay? So let's say I have a test tube, and inside of that test tube, or cuvette actually is usually what we use a cuvette. All right, what we're going to do is we're going to shine light through that cuvette. Now we know that when we shine light through, we see colors because everything is absorbed except the color which we see, which is reflected back. All right, so here's our incident wave coming through. initially, and then here is our final incidence wave. Okay. But let's say I have a cuvette, and in this cuvette, I have a much darker solution, all right? So here is my incidence wave coming in and leaving. All right, so let's compare cuvette 1 to cuvette 2. This is a darker solution. So it has a higher solution, or I'm sorry, a higher concentration. We know that through its color. Cuvette 1 has a lower concentration. It is more dilute. Okay, so let's compare here. This is going to overall be less intense because more concentration of solution, and therefore less light is allowed to pass through. So basically what we have here is we have a concentration, a cuvette that is very concentrated. And if we were to draw this at the particle level, what we see here is we have a highly concentrated solution, so lots of solute particles. The light is coming in. That light may hit a particle and be absorbed. So that's why less light comes out, because there are more particles which are going to absorb the light coming in, and it'll be harder for the light to pass through the cuvette without bumping into a particle. All right, so we have a less intense light coming out. Let's say we wanted to increase the size of the cuvette. I'm going to keep the concentration the same as it was in number 2. So here's my light coming in, and here's my light going out. All right, so I have just simply increased the size. Now I am twice as wide as number 2. Oops, as number 2. But I have the same concentration. So what's going to happen here when this light comes out? Let's compare the light of 3 to the light of 2 coming out. So the cuvette is wider, so my light has a further distance to travel. So it will bump into more particles and more light will end up being absorbed. All right. So in terms of light intensity that passes through, let's look at 1, 2, and 3. So we are looking this in terms of light intensity that passes through. So 3 is going to have the least amount of light pass through because it has the longest distance to travel and the highest concentration. 2 is going to be next because its concentration is the same as 3, but a shorter distance to travel. And then 1, where we have the shorter distance to travel and a lower concentration. So 3 is less than 2, which is less than 1. Transmittance is the ratio of light in to light out. So comparing how much light goes in to how much light goes out. Now, the higher the transmittance, the lower the absorption. So absorption is going to be those particles absorbing the light, right? Like we did in our diagram above. All right, so a light particle comes in or light hits a particle and it gets absorbed. Okay, so this is our absorption. So the more light that passes through, the lower the absorption. So absorbance is defined as how much light is absorbed by those solute particles. And we can find the transmission if we know the absorbance by doing, we can find the absorbance if we know the transmission by doing the negative log of T, for example. All right, and then you can do the opposite of that. If you have T, you can find A as well by doing 10 to the negative, all right? Just like we did in pH, that relationship there between the logarithmic, all right? And we can use this here to compare absorption and transmission. All right, so let's look at Beer's law. The formula for Beer's law is A, big A, equals little a, B, C. And what this means here is this formula says that absorbance is proportional to the path length. So absorbance so I just wrote proportional here. All right, there's our symbol for proportional to the path length of concentration. So let's dive in here and let's look at our formula. All right, so for our formula, C is our concentration of the substance. And we know that concentration is moles divided by liters. B is our length that the light travels. Which is important because we know that the length the light travels affects how much light gets absorbed. All right, so the length that the light travels, and this is in centimeters. And little a is our molar absorptivity. All right, and molar absorptivity is defined as the probability of electron movement into its excited state. And if you'll remember from honors chemistry, we learned that when we zap electrons with energy, they get excited and they can move energy levels, all right, and then they'll fall back down to ground state, emitting a wavelength of light. So our units for molar absorptivity are liters over mole times centimeters. So if we look here, liters over mole times centimeter, and let me just put this real quick, liters over mole centimeter, okay? Centimeters cancel, moles cancel, liters cancel. So this absorption here has no units. So my big A has no units because they all cancel out. So let's do an example problem. A solution of potassium permanganate has an absorbance of 0.539 when measured at 540 nanometers in a 1 centimeter cell. What is the concentration of the potassium permanganate? Prior to determining the absorbance of the unknown solution, the following calibration data was collected for the spectrophotometer. All right, a spectrophotometer is the machine we use to collect how much light gets absorbed and transmitted. So here's the data that we got from the calibration. So our first step here, in order to answer the question, it asks us, what is the concentration? So to find concentration, our first step is we have to find little a, okay? Because big A equals little a, B, C. I know the absorbance, all right? I've got all of these different absorbance levels here. So I'm going to pick an absorbance from my calibration data, and in this case, I'm just going to pick the first one just because I chose to. As long as they line up, it doesn't really matter, but all right, this is my concentration, okay? So if we had picked a different absorbance, we would have to make sure we use the appropriate concentration that goes with that absorbance, okay? So here's my absorbance. My B is the size of the cell, which it tells me is a 1 centimeter cell. And then my concentration, I know my concentration for this absorbance is 0.03. So when I plug this into my calculator, I find my little a to be 5.4 liters per centimeter mole. Now that I have my little a, I can now find C. The absorbance is provided for me in the problem. So at 540 nanometers, that's the wavelength of light we chose to use, I had an absorbance of 0.539. So I'm using my calibration data to find A. Now I'm using the data provided in the problem to find concentration. So here's the absorbance at the unknown concentration. Here's my A. And again, A equals little a, B, C. Okay, so here's my big A. My little a I found to be 5.4. My B was a 1 centimeter cell. And then my C is what I am searching for, my concentration. So when I plug this in, I find that my concentration is 0.0998 molar. And again, we're sticking here to the rule of 3. So how would we even know in a spectrophotometer what wavelength of light to choose? So we had 540. How did the scientists know to choose 540? And what we're going to do is we're going to look at our color wheel. All right. And in our color wheel, we have red, we have orange, we have yellow, we have green, we have blue, and we have violet. So again, remember the color you see is what is reflected. Everything else is being absorbed. So if I had say a blue substance, I am going to choose the color opposite of that, which is orange. Because blue is being reflected, the orange is what's actually being absorbed as the light passes through. If I had a violet, I would use yellow. If I had red, I would use green. If I had green, I would use red. All right, and it's based on the idea that we know that the color we see is reflected and the other colors get absorbed.